Shall we get started? Okay. Hey, how is assignment 1 going for everybody? I hear some sighs. What's the cause of these sighs? Shall we get started? And once you know a little bit about why GPUs are the way they are, and you know a little bit about how to write code for them, then we can dig into we can go back to some of the ideas from Lecture 2 and really look in detail about how these modern GPUs are architected. So that's what we'll do today. So if you recall from Lecture 2, we pointed out a couple of major ideas in modern parallel architectures. We talked about filling a chip full of cores. We talked about gaining further efficiency with SIMD processing. We talked about hiding forms of memory latency or even other forms of latency with some form of hardware multi-threading. Those are like the 3 ideas from that lecture. And I told you at the time that GPUs and CPUs and even other processors, like your mobile SoCs, they're all kind of just like different embodiments of those ideas. And today's lecture is no different, right? So a GPU has a bunch of cores, and they embody some of the ideas that you've been talking about on assignment 1. So does anybody know why a GPU exists at all? Like every one of our machines these days, almost, whether it be our cell phones, our desktops, our laptops, has a multi-core processor in it that would be called sort of quote-unquote a graphics processor. So why is that there? We already have a processor. Why is there an additional component of these chips for graphics? For pixel rasterization. So there's going to be some algorithms that are about drawing pictures, and those algorithms are highly well suited for this type of processor. And we're not going to talk too much actually about drawing pictures today, because this isn't a class like that. Does anybody else have anything to add? Okay, so let me just for fun, this is not material that's going to be on exam, but history is useful. Is that if those of you go take 462, which I teach from time to time, or that Keenan teaches, is you'll learn about algorithms for drawing pictures, for making pictures. And in many of these algorithms, the problem description is if I give you a 3D representation of a scene. Let's say I tell you all the surfaces are, I tell you where the lights are, where the camera is, details about materials of those surfaces. We can write a computer program that simulates how that scene would look from that virtual camera. So most of you have played some video game at some point, or seen an animated movie, a computer-generated movie at some point, and all of those algorithms boil down to, given some 3D description of a scene, how can we simulate what a real camera would see if it was in that scene? And modern GPUs today GPUs came about from trying to solve this problem. And modern GPUs today still are very good at solving this problem, right? So if you wanted to jump on YouTube today and say really amazing real-time graphics, you could see this scene, which was an output from the Unreal Engine in 2015. And this can be rendered in real time today on a pretty high-end, expensive graphics processor. Some other examples would be, like images like this. We can make some pretty nice pictures at 30 frames per second. And if any of you have taken graphics and you know how slow your renderer probably ran in 462, and you think about like what it might take to make these kind of pictures at 30 or 60 frames per second, there's quite a bit of A, code optimization, and B, just a lot of horsepower to render these kind of pictures. So like in any problem in this class, your first question should be, well, if we try to design a machine or algorithms that are run really fast in this problem, well, what's the workload? What are the characteristics of the workload? And so this gives me an opportunity in talking about that workload to give an example of when you start seeing any system in computer science, especially many of you, this is your first systems class, and you might take additional systems classes. And you might be exposed to a bunch of different systems later on in this class. And I want you to get very comfortable with sort of getting your head around a new system very, very quickly. And so I'm going to walk through this 3D graphics workload and these graphics processors, assuming that nobody has had any graphics at all. And I want you to notice how I'm describing a system so that other people can understand it without getting into the details of the implementation. So let me get started here. And the first thing I want to start with is whenever I look at a new type of hardware or a new programming system, like the first time that I saw MapReduce or I saw Spark or GraphLab or SQL, I start asking myself question, any system exists to have things, there are nouns, and then there are operations on those nouns. So what are the things that the program is manipulating, and what are the operations that the system allows me to do on those things? So let's go think about those two questions in computer graphics. So in computer graphics, the things are shockingly simple. And I can represent an object, a surface, by a mesh. And that mesh is defined as a set of triangles. And I'll more generally refer to primitives, like triangles are an instance of a primitive, but we could have lines and quadrilaterals and other things as well. But for now, an object, a surface, is going to be represented by a list of triangles. And those triangles are defined by their vertices. And their vertices are just positioned in 3D space. There's some virtual world, and that's where those triangles are. And everything I'm about to tell you about making pictures boils down to operating on only 4 different things. Vertices, which define where the corners of triangles are. Triangles, which are made from those vertices. Fragments, which represents a piece of a triangle at a particular pixel. I'm going to break those triangles up into pixel-sized chunks. And then I'm going to actually stick these pixel-sized chunks in an image and actually make colors of pixels. So if you want to think about the 3D graphics workload, you think of, what do I do to vertices? What do I do to triangles? How do I break a triangle up into these fragments? And then how do I stick colored fragments into the final output image to make a picture? That's what the whole system does. And then, so now that we have these nouns, the question is, what are the verbs? What are the operations that sort of do these things on these elements of the system? So let's just talk about rendering a picture. So I'm going to give you, as input, a list of triangles. And that list of triangles is it's just a buffer, it's just a list. And every triangle, let's say, is defined by three vertices, 3 positions. Every position is just an x, y, and z. And if I give you a list of these positions, you can go ahead and say, I'm going to take every set of 3 positions and treat that as a triangle. Here, I was actually a little bit more efficient, and I'm saying every time I give you 3 things, just kind of think about it as a sliding window. The last 3 always defines a new triangle, slightly more. Because if you look back at this picture here, you notice that different triangles share the same vertices, so it's a little bit more efficient to encode things that way. Okay, so, and then what I'm drawing here on the right as I describe the algorithm to you is I'm describing a way to think about the computation sort of as a system. So we know that at some point at the very top, there's going to be a buffer of these positions. I need to give you a list of these positions. And I can think about that list as just a stream of vertices that we need to process. A big list of vertices. So you can be thinking very data parallel right now. And then if I give you these vertices, which are just defined as 3D positions in space, something has to compute, given some camera position, where on screen that vertice would lie. So if we were standing right here and looking at it from this direction, that vertex in XYZ 3D ends up projecting to this little part on the screen, and that's where it lies. And so that's why I'm showing you I'm going from 3D to 2D. So we need to have some operation which operates on every single vertex to figure out where on screen it's going to end up. And then what I can do is I can just join these vertices up. I need some operation that takes that list of vertices and creates the triangles that I told you about. So now I'm just going to draw that too. So now I have a list of triangles. So on the right, input is a buffer. That buffer defines a stream of vertices to process. Those vertices undergo some processing to figure out where they are on screen. And then I group them together into triangles. Nothing fancy. And now once they're grouped into triangles that have like a 2D position, I can cut those triangles up into a whole bunch of little pixel-sized chunks. So now I get as input one triangle, and I get as output a whole bunch of these little pixel-sized chunks. And for every single one of those pixel-sized chunks, I need to compute the color of the surface at that position. So I'm going to compute the color. And then I'm going to stick all those pixel-sized chunks into the final image and just write to certain pixel values. And that's basically the whole computation. So does that roughly, sort of make sense, right? You can imagine that a computer could do that. And then all of the black boxes So when you guys listen to this offline, is it really scratchy? No? Okay. Because I can just hear it in my... And so if you are a graphics person, you wouldn't think about GPUs or C code or anything like that. You think about this algorithm that I just described to you as this pipeline of operations. It's called the real-time graphics pipeline if you took 462. And GPUs are designed to execute this pipeline as fast as possible. That's what GPUs are designed to do, or originally designed to do. And that pipeline, it is a programming model. In some sense, it's a domain-specific programming system that only allows me to do those kinds of things. And so you might be wondering, well, how did you compute the color of this thing? Or how did you compute the position? Like, for example, for every one of these fragments, what came in was sort of like, here's a piece of this triangle. And what came out is that piece looks like this color at this pixel. And there are many different algorithms for computing the color of a surface. For example, if I give you information about how shiny it is, or what color it is, or how scratchy it is, you might have many different little programs that can compute the output of this color. So here's an example of showing you all these different materials. And back in the early days, like when I was an undergraduate, if you wanted to say, here's the color I wanted for this material, you would use an API, for example, OpenGL or Direct3D if you programmed on a Microsoft system, and you would say, look, I want this material to be this color. I want this material to be this shiny. It needs like a highlight because it needs to look like metal. So when you make the shininess yellow or something like that. So you have this API for saying, here are the parameters of the material. And those parameters would be used in some function which would compute the color at every one of these pixels. And the same thing is true for details about the lights and stuff like that. Now, it turned out that as we got more advanced, the materials in the world are very diverse. If you look around at all the clothing that we're wearing in here, like for example, that's a very sophisticated material on your laptop there, and that like if I look on from different angles, it has a very different appearance. If you look at the handrest on your desk, you'll notice that if you look straight down, it will not look shiny at all, but if you look at it from an angle, it will actually look shiny. So its reflectivity changes based on the angle that you're looking at it, as one example. So it turned out that if we wanted to make pictures that sort of represented the diversity and the complexity of the real world, we couldn't boil it down to all materials just have these 5 parameters. And if we set the right value, the parameters were good. What we realized is that defining or simulating this really, really complex materials and light sources meant that we just had to write code. And so what happened was that this pipeline, these black boxes that I completely ignored, became yellow boxes. And the yellow boxes are places where you can inject a little function into the system, and the GPU would execute that code. So if the input came in, said, here's the vertex position, and here's some details of the surface, I would give you a function that simulated the glints off of the ruby slipper, and the output would be the color given that material. So this is how we started thinking about graphics. Is we had this pipeline, this really fixed sequence of operations that was needed to make a picture, and different parts of those black boxes all of a sudden needed to be programmable. And the details on this slide don't really matter that much, but here's an example from GLSL, which is a C-like programming language used to write these functions. And you can see what I provided as I just provided a function. I provided a side effect-free kernel. And it says, call this function every single time you need to compute the color of something. And it will return a color. In this case, a color is a vec4, which is RGB and alpha. Alpha is the transparency of the surface. So the details of this don't matter very much. But there's one thing that's kind of interesting is the inputs to this function, just for some historical details, they're not as proper arguments. They're up here. And that this varying keyword basically says that these values change. The normal, the texture coordinates, like information needed to compute the color changes per pixel. And some of the information, like the direction of the light source, is the same for all the pixels. So we had these, in some way, remember in ISPC there was this notion of uniform and non-uniform? Here, uniform is still there, and I put this word varying in front of things that would be per call as well. So the details of this function don't really matter so much. But what does matter is if I run this function on different arguments on a particular surface, if you notice that here, for those of you that have taken 462, this is the texture map I'm using. So that's like the detail that I put onto the surface to define its color. If I run this code on every single pixel, and I take the output, I might get an image that looks like this based on my various inputs. So this GPU is running these little functions on every single pixel, or actually on every single vertex as well. So the reason why GPUs have all of these high throughput cores is, in fact, to run all of these simple little kernel functions to process all the pixels or all the vertices. So given that workload description, can you see why it's very easy to make use of large numbers of cores? So what about the program that I'm giving you, or the characteristics of the task, suggest that parallelism is really easy to take advantage of here? Yeah. And then there's a few details why that's not 100% correct, but I didn't tell you. But yeah, for everything that I've told you, every single pixel on this 2-megapixel display can be computed completely in parallel. And in some sense, all the vertices can also be computed more or less completely in parallel. So I have millions or tens of millions of independent things I can work on. Yeah? In general, it turns out to be about the same, which is convenient, but there's nothing about the programming language that I just showed you that actually ensures that the case, right? Like, this is actually a C-like language. I could put a for loop in here that has dynamic branches or bounds and stuff like that. But remember, if maybe I'll have 20 cores. Maybe I'll have 1,000 cores or something like that. I have tens of millions of things to do. So even if one of those things is significantly longer than the rest, you can imagine that you could just sort of dole out work and you'll be OK. And we'll talk about that a lot more next time, actually. But you shouldn't be too worried about being able to find the parallelism. There's some other things that we'll be worried about. But so now you can kind of imagine that, like, every single time, Moore's law kicks in, and a year and a half later, we have twice as many transistors. These GPU folks at the time were like, well, shoot. Let's just build twice as many cores. And that means we can process twice as many pixels, and we can have a scene that's rendered at twice the size, or we can have twice as many triangles, and that turns into much cooler detail. And this was all kind of starting to go on roughly back, if you think back to Lecture 1, right in the early 2000s, right when the CPU architects were like, gosh, we're running out of things to help you with. we don't believe it's reasonable to force you to write parallel code. So we're going to keep trying to ramp clock, or we're going to keep trying to ramp ILP. Where is the parallelism in this program here? My conjecture is that I did not write a parallel program. Right? I just wrote this really simple function that in the context of this big graphics pipeline, I told the system, I told the graphics system, hey, here's a little sequential function. Every time you execute it on a pixel, it can be done in parallel. But I'm not going to tell you how or anything like that. I don't have to worry about locks. I don't have to worry about any of the hard stuff in parallel programming. I'm just going to write a kernel that can be applied to a sequence. In this case, the sequence is all those pixels. So this was very natural to people that had been writing graphics code. So, we were, and I say we because it was the group that I was in at Stanford at the time, and there were some folks at UW, or not UW, sorry, at the University of North Carolina, and they had been, like the senior grad students were like, I know a lot about parallel programming. This sounds like a data parallel system to me. Why can't we make it as easy to write data parallel code without all this graphics nonsense? So what they started to do, and what Ian Buck at Stanford and Mark Harris at the University of North Carolina, they just started hacking. They said, screw all this geometry and graphics, and let's just render 2 triangles that cover the entire screen. And I know by the rules of the game is that the graphics processor is going to create one of those little records, one of those little squares for every single pixel on screen. So if I wanted to run a linear algebra computation that added 2 1 million element vectors, let's just make the screen size 1 million pixels and write the add function into this little shader that I showed you before. I mean, total hack, like complete hack. And this hack kind of got some people excited, right? Like this, people were able to reduce rendering triangles to sparse lattice solvers and matrix multiplies and all this other stuff. And they were like, wow, there's so much compute sitting here in these graphics chips because they have to render all these pixels that we're able to start outperforming the CPUs of the time. Now, at some point, somebody said this is really ridiculous. We shouldn't be writing these bogus papers. And somebody tried to say, look, let's take some of the lessons that the real parallel computing guys had come up with in the 90s or even earlier, and let's see how to implement those abstractions on top of this new compute hardware. So there was a project at Stanford done by a grad student named Ian Buck. Does anybody know who Ian Buck is? Has anybody worked for Ian Buck? Hi, Ian. So Ian is the now VP at NVIDIA in charge of CUDA and all of compute. Right? So his thesis was a system called Brook. And Brook said, I'm going to take basic data parallel programming ideas that almost seem really obvious to us today, and we're going to come up with a compiler that translates programs written as sequences, streams of elements, and functions, kernels that are mapped onto those streams, down into these OpenGL draw triangles calls so we could use these really, really cheap parallel computers that people are making these days. So that's what Brook did. And then people started to say, you know what, like maybe there's something here. And so Ian went off to NVIDIA and then did this for real. And the for real is what showed up in about 2007. And before I talk about that, I have a question for you. So if I give you a processor, let's just say it has 2 cores. Let's say it's the world's simplest processor, 1 ALU per core or whatnot. And for those of you that have had operating systems, which might be a few of you, or those of you that just know this anyways, if you're the operating system, how do we actually run code on this processor? I mean, this is just a piece of silicon at this point. So what does it mean to prepare the processor so that it can actually do something useful? What does this entail? I think you talk a little bit about this in 5.13, 2.13, I believe. So if I want, this is what I would ask you as an interview question at any systems job these days, by the way. And in fact, I've seen this as an interview question. So I boot my computer. It's powered up. I double click on an icon on my desktop which launches an application. What happens next? Yeah. Okay, so first of all, we have to read the program text. We bring the program text into memory, right? Or maybe we demand page it in and whatnot. But there is a binary. Okay? That sequence of instructions is now sitting in some future process's address space. Okay, so now I just have a set of instructions in memory. What next? And we don't have to get into great detail on this, but maybe at a really, really high level, is I have code, I have bits in memory that could be interpreted as instructions. And in fact, this was important in your BOM assignment. So I want to start running that program. What does, in this case, the operating system need to do to run that program? Yeah. Okay, and how does it do that? Absolutely, I agree. So how does the operating system start running that thread? Yeah. So we need to set up an execution context, right? So the operating system is going to choose an execution context. Essentially, it's going to trap first. It's going to choose an execution context. It's going to set up the environment, set up the virtual memory mappings, and the most important one, which was what you two were alluding to, is we're going to set the program counter to point to the first instruction in main, essentially. And then at that point, we let the processor just go, and it starts executing those instructions in the instruction stream in the context of the environment that's been set up, the virtual memory mappings, and so on and so on. Okay, so it makes a lot of sense, right? You basically set up the registers on an execution context. And one of those registers is the program counter, and you tell the processor, start executing instructions. And the program tells you what to do next. Good. Okay. Now, what's interesting is that if you went back to GPUs back in the day, that's not how things worked. GPUs were processors that only executed this particular graphics pipeline. So if I wanted to run a graphics program on a graphics processor, I would tell the processor, here's your output screen size. Here's a pointer to the vertices. Here's a pointer to program text for processing pixels and for processing vertices. And then I would say, go. And the processor would start reading values out of the vertex buffer, distributing work to all of these cores, setting the PCs up itself. And this was all being done sort of by the hardware itself. So there was no way for me to run any other computation other than a computation that had the command draw triangles. That was just the way the architecture worked. So what Ian and his collaborators at NVIDIA did after he graduated and went over there in 2007 is, if we're going to start using these chips like processors, we need to make them have an interface much more like processors. And so that is what gave rise to this alternative architecture, this alternative interface to graphics processors, which these days we tend to refer to as compute mode, which is odd because it was always computing things, but as opposed to graphics mode. And now the way it works, it's actually much, much simpler than graphics. It's, here's the program text for the kernel. Here's how many times I want you to run it. And I'm going to go ahead and pre-allocate some buffers in memory that you can access if you want. Go. So it's very similar to setting up a traditional processor, except it's not start this one thread, it's run n instances of this kernel. And the way we're going to define these kernel functions, the language we're going to write in is a language called CUDA. I can't even remember what CUDA stands for now. I think it's Compute Unified Device Architecture, which means nothing. And so CUDA you can think of as NVIDIA's programming language, which is very similar to an open standards language called OpenCL. So CUDA only runs on NVIDIA GPUs. Thankfully, we have NVIDIA GPUs here. I think CUDA is actually a much easier thing to teach and write code in, so we're going to use that in class. But everything I say about CUDA has a one-to-one correspondence with just more messiness over an OpenCL. OK, so here's the plan. So I want to talk about CUDA's programming abstractions. I want to talk about how CUDA is implemented. So first, again, we're going to talk about semantics and what it means. Then we're going to talk about how that program is translated down and run on a GPU. And then last, we're going to get into a little bit of GPU architecture to just kind of have some fun. OK, so here's another caveat. Remember last lecture I was like, there's an ISPC task. There's this notion of a task that we just kind of say when we're talking. And the same thing is true of the term thread. And I apologize. So when I say thread in this lecture, I'm almost always going to mean a CUDA thread. And I mean a thread as defined by the CUDA programming language. And I'll be very clear about that. And I don't want you to confuse a CUDA thread with a P thread, because there's some very big differences in implementation, even though they're very similar in terms of abstraction. So in this lecture, when I say threads, I'm going to try and say CUDA threads as much as I can to make sure that people know what I mean. OK, so here's your first CUDA program. And you should think about the code that I'm showing you is C code with a few extensions in it. And this is very similar to the C code that I showed you that called an ISPC function. So this is normal C code with the exception of this place right here, which I've highlighted in red, because obviously it has this weird angle bracket syntax. So it can't be, it's not ANSI-C. Okay. So in ISPC, when your C code called an ISPC function, what was the meaning of that call? So in main.c, in void main, you called an ISPC function. And we went from a single-threaded control program to what? Yeah? So now we are running in ISPC speak a gang of programming instances, which in more general speak says, OK, that means that we now had n instructions, n logical sequences of control that were running. They all happen to be implemented with a single sequence of control with SIMD instructions, right? But when we looked at the program, we said, what does this program do? We said, well, it's a single-threaded control. It calls the ISPC function. That launches a gang of program instances. All of those program instances terminate, and then control returns to the original C function. That's exactly what I'm showing you here. So imagine that we had a CUDA function called matrix add, and I haven't shown that to you yet. And this is saying that we want to call matrix add, and we want to create 72 instances of it. And in this lecture, it's going to be called 72 CUDA threads. So program instances, very similar in idea to CUDA threads. The thing with CUDA is that all the threads are not flat. So you actually create blocks of threads. And in this case, my blocks of threads have 12 threads in them. And I'm creating 6 thread blocks of 12 threads each. So this is saying I'm going to call the matrix add kernel, and I'm going to create 6 thread blocks of 12 threads each. And I understand that this seems overly complex at this point, but I will come back to it in a second. Okay? And then here is what I'm showing you now at the bottom. The top is the exact same code. On the bottom is the CUDA language definition of the kernel. So this would be akin to the ISPC code now. And just like ISPC was an SPMD program, where every instance figured out what to do by accessing program index, CUDA programs can ask for their thread index within their current block and their block index over the whole set of blocks. So if you wanted in your head, and I'd be a little bit careful about this, to say that threads in a thread block are like instances in a gang, and that blocks in this whole big launch of blocks are like tasks in ISPC, and you can get the task ID as well as the program index, that would be a reasonable connection to make in your head right now. Okay. So whereas in ISPC we launched gangs with a call, and we launched tasks with a launch, here we're doing them together at the same time in this one triple angle bracket syntax. And that this global function is indicating that this is code that runs on a CUDA device, which you can think of in this lecture as a GPU. You could imagine that somebody could implement CUDA on a CPU in the future if they wanted to, but all modern CUDA implementations run on NVIDIA GPUs. And that's just the normal C code. OK, so the rough outline of the structure of the code makes sense. And what is this code doing? What's it doing? It's just adding up element by element two different matrices, right? Two different 2D arrays. And so just to clarify, code on the bottom, SPMD execution on a GPU, code on the top, serial execution on a normal CPU or on the host processor. Make sense? SPMD program. Now, what do you think happens? So in this particular case, I said I wanted, let's say my matrices were 12 by 6. That's what this, I set this program up so that my matrices were of dimensionality 12 by 6, right? 72 element matrices. What if I decide to say that number of threads per block times number of blocks is not 72? Which I can do, because I can just change those numbers, right? So I can do something like this. So let's say that my matrices are now 55 elements. So they're 11 by 5. I can still set the number of threads per block to be 12. And notice that I had to round up to create a bunch of blocks. And then I had to have an if statement here to do something. So what is this if statement doing as a self-check on whether or not you're following the lecture so far? So I created in this call right here, how many CUDA threads? 72. I've written a program that more or less says that every thread will correspond to one element of the input array, and add up the two elements from the two input arrays and produce an output, right? So I have 72 threads working on input matrices that are of size 55 elements. And what did you see me do in this code? Yeah. I'm trying to not run off the end of the array. Right? So this is just a little bit of CUDA mechanics. Is you should, even though you can kind of think about the program that I've written as it is a kernel and it's applied to every element of the matrix, I want you to be absolutely clear that this is a very SPMD way of thinking. A CUDA program launches CUDA threads, organizes them into thread blocks, and you can use your thread ID to do whatever you want. In the same way that an ISPC program launches program instances, and you can use your program index to do whatever you want. So I can write a piece of code that segfaults by a kernel accessing memory that it's not supposed to. OK, so unlike ISPC, CUDA is very, very particular about where stuff is running. It's supposed to be very explicit. When am I using the GPU? When am I not using the GPU? And that's also very true of where memory sits. So we have a host, which executes serially. That's your CPU most of the time. We have a CUDA device, which is over here on the GPU. And that kernels run on the device, and the main application runs on the host. And that the host and the device have different address spaces. So if I'm running my C code, I can dereference a pointer foo and grab the data. But for my C code, I can't dereference a GPU pointer because that's over there off on the GPU. So CUDA makes a very strong distinction between memory that's allocated in the host address space and memory that's allocated in the device's address space, which can be accessed from kernels. And if I want to move data from one side of the fence to the other, my C program might allocate data with malloc right here, or new in this case, in C++, and I fill it in. And then my C program can also allocate data in this other address space. And if we want to move data from the process's address space on the host to the address space that can be accessed by these GPU kernels, we will have to move that data with a particular memcopy. So this is saying copy from pointer A on the host. That's this guy up there. It's just a normal C pointer. To pointer device A, which is a pointer into the GPU's address space, and copy this number of bytes. And there's an extra parameter which says this is the direction the data is going. It's an optional parameter. So I have here a little comment which says if the C program tried to dereference the pointer device A, it very well might segfault, or it may get garbage. And why is that the case? A little bit of you be careful here. So this is a program. This is C code. This is running within a normal C process on the host. That's correct. So the device, the allocation here is in an address space that is not accessible to the CPU. Now, in modern CUDA, there are some ways to share pointers between the GPU and the CPU, but I'm not going to talk about those here, because I think it's easier to think about the explicit case first. So if I dereference this pointer, that's a pointer in some other processor, in this case, the GPU's address space. That's junk from the perspective of the host. So you very well might segfault. So what does CUDA memcopy remind you of if I go back to the lecture of shared address space programming versus distributed address space programming or message passing? It sort of is almost a message. It's saying, take this part of my address space and bulk copy it into this address space so that the GPU can now start accessing that data. I like to think about it as a big message. And CUDA also differentiates a couple of other address spaces that I think will probably require you to do your homework to really get your head around completely. So there's memory that's accessible to the CPU. There's memory that's available to any CUDA thread running on the GPU. And then there's other memory pools that are localized to specific groups of threads. So a thread block has its own memory that it can exchange and share data with. And a thread has its own private memory that it can exchange and share data with. So CUDA has made it very explicit that in your program, you decide, I want everybody to communicate through this address space, through global memory on the GPU. I want only the threads in a thread block to be able to communicate with these addresses. And then I want these addresses to be completely private to this particular address space. Now, why do you think that they might have gone to all this trouble? Because this is more complicated, right? Like when you put code, when you allocate memory on the CPU, you just allocate memory and you hope that the caches will take over and do things. Do you have a sense, before we get more into details, why this might have been a design decision that the CUDA folks decided to make? So you can imagine that if the system knows up front that only these threads are going to touch these variables, and only these threads are going to touch these variables, that might be very helpful information in how to build, to schedule, to assign threads to cores, or in fact, very helpful information about how to not implement things that a modern CPU has to implement, such as allowing every core to be able to access every memory location in the machine, right? So there's some efficiencies we can gain from this type of information. OK, so let's get into a really simple example. And the simple example I want to choose is implementing a 1D convolution. And I want to do 1D because I don't want to do 2D. 2D would be an image blur and be a little bit more code. Here, just imagine you just have a 1D image, and you're trying to blur it. And so the output, every output element is just the average of its input element, of the surrounding input elements in the input array. Okay. So it's not quite one-to-one like that matrix add. It's many-to-one a little bit. So let me write my CUDA program. And so here's my really, really simple CUDA program. So on the host side, on my CPU side, I say, OK, let's just say that it's a 1,000,000 element array. N is 1,000,000. I'm going to allocate 1,000,000 plus 2 and 1,000,000 for my output. And then I'm going to call the kernel with threads per block, which I just hard-coded to 128 for now. I made that decision for a reason I will talk to you in a second. And then how many blocks did I need to do all the work? So if every CUDA thread is going to be managing one output, I need 1,000,000 CUDA threads, right? And so what is this doing here? Threads, why did I say n over threads per block? Let's assume this divides equally for simplicity. So what is this doing? I'm just saying I make enough blocks. And if I want to make the analogy back to ISPC, I want to create enough tasks such that every single one of these CUDA thread blocks or ISPC tasks processes 128 things. Because 128 things is similar to my gang size, and we'll talk about that in a little bit. Okay. And every thread does what? Every thread carries out exactly this logic. Every thread carries out exactly this logic. And you see that right here. For I equals 0 to 3, result plus equals index plus I. And index came from my thread ID, which was computed by what block am I times what thread am I in the block. Now, you might be wondering right now, why is there this two-level hierarchy to anything? This program would have been just as easily written with a single thread ID, right? And that's absolutely true given all the information that I've given you. So does everybody see how this program correctly computes the convolution? Correctly computes the convolution. If you don't see how this correctly computes the convolution, that all million elements are output, raise your hand and let's talk about it really quickly. So everybody's good? No? No, not everybody's good. Okay. So here's a question. What happens at this call? How would you, in an English description, describe what happens here? I'm running a C program. I've made two big allocations. Those allocations happen to sit in the GPU's memory rather than in local memory or in local device memory. I've defined a program which runs in SPND fashion that accesses its input parameters according to essentially a thread ID. I'm running one thread of control at this point. I make a call to a CUDA kernel. Instead of an ISDC task, I make a call to a CUDA kernel. What happens now? What happens now? Somebody help me out. Go for it. So now control transfers, and we don't even have to think about the details, but control transfers into CUDA. CUDA is going to instantiate and run concurrently, or has the at least has the option to run concurrently. This many thread blocks, of which every one of those blocks have 128 instances. So at this point, I begin running all of those CUDA threads. 1 million CUDA threads grouped into blocks of size 128. When all of those CUDA threads complete whatever they're told to do by this function, this definition, control returns to the caller, and we proceed. So now, can everybody see why this will correctly, regardless of GPU or CPU or anything, why this correctly computes the convolution that I want it to? Yes? You don't even have to think about GPU or CPU at this point. The only actual differentiation is that this kernel needs to run on data that is allocated in the address space that it can access. And that was done properly here. So if this happened to be implemented completely on the CPU, if you wanted to have your own CUDA runtime that decided to do it that way, that's perfectly valid in accordance with the semantics of CUDA. Now, CUDA is only implemented on the GPU right now. So you could think about this as this is the point where control transfers from the CPU thread to the 1 million GPU CUDA threads that all perform this logic. And when all of 1 million GPU CUDA threads have completed, control returns back to the CPU. Make sense? Yes? Exactly that. Well, I would prefer not to think about the hardware implementation details until everybody can confirm to me that they know what the program does. And we will go in great detail in a second about the hardware implementation details. But does anybody have any problems with what the program is doing? No. OK, so we can move on. Now, I'm going to rewrite the program. And in fact, on modern implementations, my rewrite is actually going to be a little bit more efficient. And it's going to show off why it can be useful to group threads into groups before we go any farther. So this is the exact same. The program does the exact same thing. But now I'm going to use shared memory a little bit. And before, actually, here's a question. How many accesses to input are done by this launch of 1 million CUDA threads in aggregate across all of those threads? How many load instructions are going to get executed? Let's just assume that one line of code. How many? 3 per thread. So in general, overall, how many? 3 million. Correct. Okay. So I'm going to rewrite this program just a little bit. And the only thing I want you to look at right now is that red line of code at the top. So before, we only had 2 types of variables. This is back to the old thing. We had variables that were sort of uniform, meaning the global memory input arrays, where there was one pointer for all threads and they accessed a different element. And then we had local variables per thread, like index is a per thread variable, and the loop counter I is a per thread variable, right? Now I'm going to add a new type of variable. And so those corresponded in ISPC to uniform and regular local variables. Now I'm going to add a new type of variable, which is variables that sit in the local address space that can be accessed only by threads in the same block. So what I decided to do up there is I added this keyword shared. So what that means is that there is one instance of that allocation per block of CUDA threads. So if a uniform variable, there is one instance of allocation for the entire program. For a per block shared allocation, there's one instance for the whole block. So now I have 3 levels of frequencies going on here. So now if I go back to my original CUDA program, keep in mind that two adjacent CUDA threads, or 2 threads that are producing adjacent elements of output, will issue load instructions to the same data, right? 2 of the 3 input elements that they need are shared. So if I want to optimize my code a little bit, I can start taking advantage of that. So even though I have the answer on the slide, I actually want somebody to tell me what this program is doing, because I will say that the 128 threads in a block are together cooperating. I've written the program so that they cooperate to significantly reduce the number of load instructions that actually need to be issued by this program. So take a look at it a little bit, and I actually would prefer that you figure this out on your own. This is helpful. So take a look at your friendly neighbor, and let's spend like 30 seconds just talking about what in the world is this program doing, and I'll go ahead and tell you that sync threads is just CUDA's command for a barrier. And it's a barrier across all the threads in a thread block. Okay, so talk it over for like 1 minute. Okay, so I'm going to go ahead and stop. So first of all, is CUDA a high-level functional language, or is CUDA a pretty low-level C-like language? It's meant to be a pretty low-level SPMD C-like language. So who can give me a gist of what this program is doing? Yeah. Correct. Uh-huh. Yep. Okay. So before you keep going, let me stop and let's summarize a little bit. So first of all, we kind of went from thinking about this program of what does every thread do, which is how the last slide was about, right? Every thread reads 3 values, average them, and outputs a value, into thinking, what does every thread block do? And so we said, oh, look, every thread block has 128 threads. It needs it's going to have 128 outputs. And that means it needs 130 inputs, right? So, okay, so let's figure out how all of the threads in the thread block can work together to load those 130 inputs that they all together need. And so let's talk me through a little bit how the thread block loads those 130 inputs. So we needed to load 130 values. We had 128 threads. We decided to have all of the threads load a unique value to get the first 128. And then we kind of had a workload imbalance problem. We needed 2 more. So we had the first 2 threads in the block. Go ahead and grab the last 2. And then, now keep in mind that all of these CUDA threads are running concurrently, or at least have the semantics of potentially being able to run concurrently. So those 128 threads completely in parallel might have actually issued all those load instructions. And then what is the barrier here for? So sync thread says barrier all of the threads in a thread block. So we are guaranteed that all 128 threads have arrived at this statement when that call returns. So that means now that exactly every single thread after the call to CUDA sync threads is guaranteed that any prior instructions by any thread in the thread block have completed, which means that all threads have loaded the data into shared memory as necessary. And now the program can proceed as the first one did, except now the access to the data is out of shared memory rather than out of global memory. So who thinks which program is better? Which program issues more instructions? Which one? Well, this program actually definitely issues more instructions. It actually issues far fewer load instructions, actually. And it turns out that, I'm going to bring up an implementation detail now, is that the access to this shared memory variables can be made very, very fast, which means that you can think about multiple accesses to that shared memory as, in general, on most NVIDIA GPUs being significantly faster than multiple accesses to global memory, even if the global memory has a cache. And I'd love for somebody to actually write these 2 programs and post what their performance observations are in writing these programs. Okay. So CUDA gives you a number of primitives to start thinking almost in a shared address space way. For example, we have a barrier amongst all the threads in a thread block. We have various atomic operations for read, modify, writing variables in global memory or in shared memory. And there's various types of ways to synchronize the host and the device. So in your head at this point, you should be thinking, OK, CUDA is pretty much like every ISPC or any other programming system that we've said that's SPMD. Except there's this little wrinkle that they decided to group the instances of the CUDA threads into these blocks, which can be convenient because now blocks can have per block allocations that allow those threads to communicate very, very efficiently. And on a big machine, dividing problems into subproblems and making sure that the threads working on the subproblem are right next to each other and can communicate efficiently might be very useful. That's basically the whole rationale. OK, so let's check our understanding here. Here's that program, exact same program of 4. This is the second version of it, second version of the program. Now, I want you to think about this call right here. And I said this creates 1 million CUDA threads. And I want you to think about changing this to a for loop for I equals 0 to 1 million pthread create. And if I did that, it will pthread. I would create 1 million pthreads. I would create 1 million pthread stacks, and so on and so on, right? So do you think running this CUDA program will create 1 million instances of local variables for every single one of these threads? And do you think it will create 8,000 instances, because 1 million divided by 128 is about 8K? Do you think it'll create 8,000 instances of the float shared support memory? It would be a valid implementation. It would absolutely be a valid implementation. And it's a perfectly reasonable way for you to think about how the code runs, actually, in some sense, because it is a valid implementation. Now, who thinks that it's actually implemented that way? How do you think it might be implemented? You want to add? Yeah. But this program, I said that this creates 1 million concurrent CUDA threads. And so it seems to me like I need to create 1 million thread stacks. I just need to allocate them up front. So if I'm going to concurrently execute 1 million threads, yeah. I said something about the semantics are a little bit unclear, right? Because I didn't say there are 1 million independent threads, because they're not independent. Because I just showed you that they barrier and do all these other things. I kind of said concurrent because they should all be running at the same time. Any of them can be running roughly at the same time. So let's go think about what this actually really means as we go forward. So I think everybody would agree that they would love to be able to run this program with no change on, let's say, a big, honking, expensive GPU with 16 cores, or a really mini GPU with like 6 cores, or maybe even the GPU in my laptop or in my iPhone with 1 core. Okay. So the semantics need to be sufficient for me to have the flexibility to run them on 1 core serially or on a ton of cores in parallel, so I can use whatever machine I have really efficiently. So let's talk about how this works. Again, this is all the same program. And now keep in mind that when we compile this program, we're going to get out some program text. We're going to get out a sequence of instructions that says what every CUDA thread should be. And we're going to get out a little bit of extra metadata. And that metadata is going to say things like, well, this program needs to be run with 128 threads per block. This program needs B bytes or some amount of shared memory. It also could be it needs this many bytes of local memory or something like that. So when I compile the program, I'm going to have a little bit of extra information about its allocation requirements. And if I have a GPU, let's say it's a 4-core GPU, any modern GPU in it, if you remember back a couple slides, the command I make to the GPU, the command that software makes to the hardware, is run this program text that needs 128 threads per block, needs 512 bytes of shared memory or whatever. Run it on 8,000 blocks. That is the command that goes to the architecture. And so maybe an instance of that architecture is a GPU with 4 cores. So the GPU is now responsible, the driver or the hardware itself, is responsible for divvying up these 8,000 thread blocks in this example to these 4 cores. So there's no way that a CUDA assumption, a CUDA program, cannot make the assumption that all of the thread blocks are running at the same time. Because otherwise, we could not take a CUDA program and run it on a small machine, a big machine, and so on. So when I say that all of these CUDA threads are running concurrently, I really actually am saying all of the thread blocks need to be independent, or need to be able to be scheduled in any order, serially or in parallel. And that's the requirement of that launch. And so this pattern of I have 4 cores, I have this huge list of thread blocks, should be very familiar to you if you think about ISPC tasks, right? And this is a common pattern you're going to see in any parallel system. As we decompose a problem into all of these bit pieces, we only have a certain number of workers, and we need somebody, either a software scheduler or a hardware scheduler, which in the GPU it really is hardware, that takes a look at this list of tasks and says, oh, you do this, you do this. Oh, you're done? Here, have another one, and so on and so on. Other examples would be ISPC's tasks. If you're implementing Apache in a web server, you might have a pool of threads that handle all these requests. You'll see this pattern all over the place. OK, so now let's start talking a little bit about implementation. Okay? And this is where things are going to get kind of fun, because one of those cores on a modern NVIDIA GPU looks a little bit like this. So this is my cartoon diagram of the GTX 1080 core that's in your lab. So in some sense, it's very, very familiar, just like Lecture 2, right? I have a bunch of SIMD ALUs. I have 32 wide SIMD ALUs. I have the ability to select up to 4 execution contexts to run at once. And out of each of those execution contexts, I can pick 2 instructions. So I have 2 wide ILP, 4 wide simultaneous multi-threading, and I have up to 64 execution contexts I can choose from at any one clock. And I change my terminology here now to match NVIDIA's terminology, where they refer to one of these execution contexts for an instruction stream as a warp. And we'll get back to that in a second. So I'm now using this term warp to mean very much like a CPU thread. So I have 64 warps that I can interleave. Every clock, I'm going to pick 4 of them. Out of those 4 warps, I can execute up to 2 instructions. And as you can see from the diagram, I can only choose 2 instructions if one happens to be a normal arithmetic instruction, and the other happens to be a, typo. Sorry, 1 second. This is a load store. OK, fixed. Is if one of those instructions is sort of a normal arithmetic instruction, and the other is a load store or some fancy sine cosine or something like that. Yeah. About a warp? Yep. Yep. I'm going to go through that in 1 second, and I think it might be most clear if I go right here. So let's talk about how this CUDA program runs on this core. And I want you to think about how a thread block will run on this core. So a thread block is 128 CUDA threads. 128 CUDA threads, groups of 32, will share an instruction stream. Now, what I'm talking about now, I want to be absolutely clear, is now I'm talking about implementation details. There is nothing in CUDA that says this has to be true. So threads 0 through 31 in this instruction, in this thread block, are going to get mapped to ALU 0 through 31, and will share an instruction stream. So a warp, or a group of 32 CUDA threads, is very, very similar to what in ISPC? That is a gang. So there's actually not a thread block gang correspondence. There's actually a warp gang correspondence. Okay. So the convolved thread block is executed by 4 warps, and that's how I get the 128 total CUDA threads. So it's very possible on this modern GPU that all of the threads in the thread block could actually be running at the same time, right? Because there's 4 threads in the thread block, 4 warps. Sorry, 4 warps in the thread block. I can choose all 4 of them to run on the chip at once, and I can execute a 32-wide SIMD instruction to make progress on all 32 CUDA threads at once. So can you see how that sort of works? And each one of these cores can interleave up to 64 of these warps. So that means that in this program, I can have 16 different thread blocks being interleaved on this one core all at once. OK, so given this explanation, what is a warp? We know what a CUDA thread is. A CUDA thread is just a logical thread of control that I defined in my CUDA program. What is a warp? Sorry? Who wants to help me with this? What is a warp? First of all, is warp defined by CUDA, or is warp defined by the implementation of CUDA? The implementation of CUDA. You will see warp in a CUDA programmer's manual, but that's for implementation bleeding through abstraction. But In general, there's no such thing as a warp in CUDA. So what is a warp? Yes, and from the perspective of the hardware, what is a warp? That's almost from the perspective of, from a CUDA programmer's perspective, a warp are 32 CUDA threads that happen to share an instruction stream, which means if you put an if statement in your program and the CUDA threads go in different directions down the if statement, you will get divergence. If you're a hardware architect, what's a warp? It's an independent instruction stream and the associated state with it. So a warp, you almost certainly want to think of as a hardware thread in the CPU world. If an Intel hyper-threaded processor can handle 2 threads, and a modern NVIDIA GPU interleaves 64 threads. Exactly. So there's an implementation detail. We've talked about what is implemented. And if I wanted to think about breaking up the execution context on a core, I can think about there being room for thousands of threads, or I can think about there being room for 64 warps. You can think about it either way, which would be perfectly fine. OK. And so we went through this. Is that in a thread block, threads with adjacent thread IDs are going to be mapped into the same warp. It's not like they're going to randomly assign threads to warps, because then you don't know what's going on with SIMD divergence. So a thread block with 256 CUDA threads is mapped to 8 warps. Given the processor design that I just showed you, if I have a thread block of size 256 that needs 8 warps to run, can all of the CUDA threads be simultaneously running on this core? Yes or no? No, because how many CUDA threads can I simultaneously execute? Only 128, exactly. Can I concurrently execute 256 threads? Correct, right? I can just start interleaving their execution. Good. OK. So now to keep in mind, there's 20 of those on this GPU. Yes? It's a great question. I can jump ahead and ask the question. No, that's not it. There we go. Why must CUDA allocate execution context for all threads in the block? So the question is, why do we need the barrier, given that this is a thread block of 128 threads? So I'm going right to the question. It's an excellent question. So CUDA reserves the right to run threads in whatever order it chooses. So what happens if I decided to run all of warp 1 to conclusion before running warp 2, 3, or 4 in this thread block? And this example really gives it to you. So imagine, in this case, we had a thread block with 256 threads. Or actually, so first of all, imagine it's 128 threads, like the original example. It would be a valid program if sync threads was not in that program, not in the program on the right. I could very well choose, and I mean the GPU implementer, to run warp 0, threads 0 through 32, all the way to completion before I decide to run any of the other threads in the thread block. That would be a perfectly valid schedule. Does that make sense? Now, what would go wrong if I executed the program in that perfectly valid way, assuming that sync threads is not there? So I can execute threads in a thread block in any order that I want. I'll get back to that in 1 second, and let me get to this question really quickly. Yeah, actually it does. So you could assume that that shared memory allocation just goes out of scope at the end of the thread block. Yeah. this program is written assuming that when I run everything underneath the sync threads, when that code is executed, all threads have completed their work to bring the appropriate data into that shared memory. So sync threads is a constraint on the scheduler to tell the scheduler that that must occur. All of the threads must run to this point before we keep going. So if I did not put sync threads there, the scheduler, it would be a valid schedule to run all of threads 0 through 31 through the program, terminate those threads, and then try and run the rest of the threads. And if that's the case, the threads on the boundary between those two warps are going to assume that data is there that is not. So here's an interesting question. What happens? So now let's change this to a 256 thread block. Okay, so just take the 128 threads, let's just make it bigger to 256. And imagine that we're running on a core with 4 warps. Four warps, 128 threads worth of work. Okay, so I just shrunk. I told you that the real course has support for 64. But now say fictitiously, let's assume that we only have 4. Can I run a thread block that needs 8 warps on a core that only supports 4? And if I can you give me a method for handling it? Because I just told you that I could run 1,000,000 thread blocks on a GPU that had 1 core. But I'm specifically asking now, can I run a kernel that needs 8 warps on a core that only supports 4? Yeah. Sure, but that's a different program. So I'm saying, can I run this program on this processor? Why not? Why can't I just run, how about I just run the first 128 threads to completion, and then I'll do the next 128 threads. So you can see, like, for the same reason that I needed all the threads to run to that sync threads, CUDA is going to assume, the semantics of CUDA, that all the threads in a thread block are actually live and running concurrently at the same time on a core. Whereas across thread blocks, there's no assumption at all about what the requirements for scheduling are going to be. So in the last 2 minutes, what I'm going to do is I'm just going to go through very, very quickly how we might schedule this convolved thing, this program, on a GPU with only 2 cores. So here's a GPU with 2 cores and support for 12 warps per core, or 384 CUDA contexts. And imagine that my CUDA launch says that, hey, we need 1,000 thread blocks to be run. 1,000 thread blocks to be run. Every thread block needs 512 bytes of shared memory, and every thread block has 128 CUDA threads. I have a GPU with 2 cores, support for 384 CUDA threads, and shared memory, like let's say a really small one, like 1.5 kilobytes of storage. So now you're the hardware scheduler. You just got a job saying, run these 1,000 thread blocks. What do you do now? And we'll do it really quickly in like 90 seconds and get out of here on time. So how are you going to start allocating work to the available workers? What's the first thing you can do? We need to get started. We need to get this job done. We have to run 1,000 thread blocks of the convolved kernel. I have 2 cores worth of resources to burn. How are we going to assign thread blocks to cores? What's the first thing you might do? Start helping me fill up the machine. You're writing a scheduler. Yeah. Each block is 4 warps. So first of all, we'll put block 1 over here, and we grab some resources. We grab the first 4 warps, CUDA thread context 0 through 128. We grab 512 bytes of shared memory. OK? Now let's go ahead and keep going, right? Let's go ahead and fill up. I decided to interleave rather than fill up. So block 1 can go here. So are we done, or can we put more work on the machine, or do we have to wait for these thread blocks to complete? We can put more work on the machine, so let's just keep filling it up. First 4 thread blocks are now being interleaved on these 2 processors. OK, can I put more work on the machine? Some people say no, some people say yes. Why no? Because we actually don't have enough shared memory allocation. We actually had the execution context. We had the registers. But we actually cannot we cannot support the allocation. So we'll stop. When can we make progress again? So one of those thread blocks completes. Let's say it's that one. It was block 0. Okay, so now we can fill up. We can just take those resources and give them to block 4. Let's say that block 2 completed. Notice that these things are completing out of order. We can just fill it up, and so on, and so on, and so on. So the hardware scheduler is just saying, as long as there's resources, I'm going to give thread blocks to available processors. And when we run out of resources, we'll wait. And as soon as thread blocks come off the processors, we'll start handing more work to the rest of the processors. And that's where I'm going to stop today. I believe Professor Bryant has office hours after class. Feel free to come find me as well if you have any final questions about the homework.